Hi, let me present you some examples on the design of microcontroller-based finite state machines. Right? For instance, let's start with something like this that is nothing but a counter BCD one digit, a circuit that you know very well from P7, okay? So let's redesign it this time from this P10 perspective. And this means that you have the same block that works the same way and has the same, function table, but, using this plan again, plan X, state enumeration, but this time using, an architecture based on a microcontroller. So we will talk just a little bit about the planning, but this is the most important thing here. But we will cover that in other lessons. But in some way, from the planning, we will develop hardware and software sections. So we will be able to start a new project in MPLAB and in Proteus, so that we will capture the schematic and we will develop the C code so that we can compile it into an executable file to be attached to a simulation circuit, and so we'll be able to run Proteus simulator to get results and to check, for example, if this is the same state diagram or the same timing diagram that is obtained, right? So naturally, in this way, there are a lot of considerations, okay? For example, if we focus the attention in this counter BCD one digit, then we can focus the same attention to the counter, for example, modulo 1572, solved by means of the plan Y, and there you can ask the same kind of questions and you can solve the same kind of experiments. So these kind of questions of interest and lab exercises can be repeated twice for both exercises in this tutorial, right? And if you think about the component, naturally what goes first is the specifications, then the plan, and then this combined developing and test, okay, using the tutorials files that are available in our web, the same way as we did in P9. So it's again a repetition of the developing and test of, in this case, using again some tutorials. The plan is, as you see here, the adaptation of the finite state machine. And this is a large plan and very detailed. This is what you will find there. And with more than 12, 13, 15 figures, and, the specifications is the same as the P7. So this is the easiest part, because in this way we save time trying to adapt the same circuit that was invented before, but simply hardware. Now by software is in some way, a fashion to save some time. But the same way that you are inventing a counter, you can invent anything else, like a traffic light controller, or a light or LED sequencer, or a timer. Whatever you have in mind can be developed in the same way. So this is what you see here. If you have another counter in mind, you can follow the same stuff, the same line, the same guidelines, and the same list of bullet questions and experiments, one after the other. You can repeat that again for the other counter that you have in mind. So it's about this, okay? And in this way you can see very well which is the difference and why the programs are slightly different, and which is what is consisting this difference between the plans. So through this tutorial we will solve a lot of questions, okay? For example, how does this finite state adaptation to C works? Then another important issue here is how to trigger external interrupts. What kind of interrupt logic the microcontroller has. So how this flag, the interrupt 0 interrupt flag, the external interrupt 0 flag is settled. How this happens? What kind of circuit is there to do that kind of setting this flag? so that you can jump to the interrupt service routine, and there is where you are setting your software flag that is to be used in the state diagram resolution. And then the usual questions about a tutorial: start a new MPLAB project, compile it, setting the compiler options, for example C90 and COF output files, so that you get the two files, the COF and the HEX. You know that the COF is the one used when debugging, okay? When debugging, you have to use the COF because it's larger and contains information of symbol list and variable names and many things that are not in the HEX. The HEX is the final one that is downloaded into the prototyping board using a programmer. So then you can see in which way you can attach the COF file to the PIC18F4520 available in Proteus, the hardware circuit, and run simulations. And once the circuit is running, naturally, you can debug if there is any problem in the software or any wire connection in the hardware. So it's your time to go debugging and just making some measurements. For example, you can debug using watch windows and inspecting and following the values of the RAM variables. You can run step by step the code execution, and then you can measure, for example, how long does it take to execute the loop, the main loop, for example, using breakpoints. And that is the same idea that you can follow in order to get information about the interrupt. You see, how long does it take to get an interrupt, to jump to an interrupt service routine? So in this way you are sure that all the edges, the signals of interest, are detected because they develop an interrupt. And then logically, this is in some way a tutorial example. It is all complete. So what is recommended here is for you to go and modify the examples in some way or another. Add new features. For example, if this is a NAP counter, you can very well transform it into a add and down counter. You can make it reversible. Things like that, okay? These things are up to you because this is a never-ending story. You will never end of imagining new and different circuits all the time. Okay? The project that we intend to implement is that it is here as a finite state machine, okay, using the plan X, as we did in P7, the same chip. So the same one-digit BCD counter with count enable and terminal count. This is what is that we have in mind. And as usual, we like to think that this exists for real in the industry, okay? For example, like this, like the 74190 chip. And well, to make it easy, we will consider that now the data in and so the up and down and the load are not necessary now in this first stage. So only count enable active low and the clock and the reset and the terminal count. So this is the terminal count that we rename TC10 that way. So later on, if you like, you can implement the full chip if this is what you want. For example, changing the plan. Okay, so this kind of stuff. The data in can be conceived using the plan Y as another similar example. So here is the symbol and the function table, and then the timing diagram. As you know, you see the counter. If you let the system go counting up, what you've got, if you let the system go counting up, what you've got is the count enable to be sampled 1, and so the machine goes counting 0, 1, 2. But if the count enable is sampled on the rising edge of the clock, as usual. 0, the count is repeated. So you have a 3, and then you have a 3 again, and then you have another time. Another time means another full clock period. That's the way it works. And then if finally you sample again a 1 in count enable, you go advancing, and this goes that way until you get the last state, and then the 0 again for another full clock period. And if by any chance, when the system is counting the last state, the 9, you change the value of the count enable, you see, you change the level of the signal, this is reflected in the terminal count 10 signal. Okay, so the terminal count happens to be 1 only when there is the last state in the count, and count enable happens to be 1 the same. Only in this case you have TC10 high. In other circumstances you have the TC10 that goes down this way. All right, so yes, it is true, this TC10 output is not synchronous. You see, the Q is a synchronous signal. If the Q has to change, it has to be when you have a rising edge from the clock, but not TC10. TC10 is different. It is sensitive to the shape of the count enable. All right, that's the difference. So this is what we have in mind. Okay, this is what we have in mind. So the next step is to talk about how to plan that thing, not now as we did in P7, but as we are going to do now in P10, using a microcontroller. So in some way, you can see the picture of the state diagram, and it's not different in any way. You have 10 states. You can label them all as usual. All right, it is that the way to go through. You can label the states as usual, state 0 or num 0, just to give it a name, a label. And then you can imagine that you can stay in the same state, or you can go to the next, depending on the signals that are advancing the next state logic. Okay, this time, however, the big difference is that the signals are not anymore voltages. What you see here is not a voltage anymore, but a variable in the RAM memory. That is what you see. Whatever it is, a level sensitive variable, right? Like this one, this is a variable that you will read, or instead, this is a flag that you will detect by means of an interrupt. That is the big difference here, okay? So you know that if this is a counter, every single arrow, okay, like this one, is going to happen, or like this one, is going to be assessed because you have a given condition of the variable count enable, and remember, because you have detected a clock rising edge or falling edge. Doesn't matter the way you have configured the edge that is active. If it's the rising edge, all right. So this means that you have to detect that situation as well as you are reading the signal. And to do that detection, you know that you have to go through what is understood as an interrupt to the main program. We will develop that further now on. But you know, to detect this rising edge of the clock in this circuit, in the end, the bar clock flag has to be set high. That is what has to happen in this kind of circuits, okay? But apart from that, you see that everything is the same. In every state, you have, as usual, in different colors, a bracket that tells you the variable value for that corresponds to this state, that way. And perhaps the situation is a little bit different in the state 9, because here you see you have to describe that situation of the TC10, the bar TC10, as we said before. If it's going to be 1 only, if this is the situation, you are at the state 9 now, and the variable containable is 1. That is the situation. Okay, so you can go and study this state diagram, because this is what you have to do. And then, you know, the most important thing here is to talk about interrupts. Perhaps that is where we have to spend some time. And the interrupt is explained by means of this logic diagram and by means of this picture. Perhaps this is the best way to start, talking about this picture here, okay? So that is what is going to happen in this circuit. That's simple. You are in a main loop. You see, this is what you are, in a main loop, reading inputs, solving the state logic, solving the output logic, and writing the pins. This is what you do all the time in all these kind of examples related to finite state machines, because state logic and output logic determines, you know, it's the truth table belonging to the state logic and the output logic. So doing that at higher speed, in some way you are solving a finite state machine. Well, with the condition that you first has to read the inputs that are level sensitive, like you may imagine containable in this example. All right, and the variables that you generate, like the bar BCD code, has to be translated by means of write outputs into a pin value of 5 volts or 0 volts. But apart from this hardware adaptation, what you do here is all the time the state logic in that way. Well, apart from the initialization that happens only once when you click the clear direct, and this means going to the first memory position, and then there is the idea that you see it's all the time in the main loop. However, time to time, you see, for example, at this time t1, it happens that the system is executing I don't know what inside the write outputs. It is writing some pins, but now is when the system is interrupted. So the system jumps to execute another kind of function that is not here in the main loop. It's set aside. It is called the interrupt service routine. To do what exactly? Well, a very few things. What we have in mind by means of this interrupt that you see that takes you out of the main loop, and this is something that you don't like to, because being in the main loop means that you are executing the finite state machine. So for a brief period of time, or some microseconds, you jump to attend an interrupt service routine, so that you here has a job to do, and that job is simply to set the flag high, you see, and this flag is going to be kept high until it is used in the main loop. So what is the meaning of this? Well, later on, you see, the system go back to the place where we were just an instruction after, and continues the execution of the main loop, you see, and later on the system starts again executing the first instructions in read inputs, and there is a time in the state logic when this variable makes sense. You see, for example, to execute this state transition, you say if bar clock flag happens to be 1, go to this next state. So this is where this variable clock or start flag, whatever it is, depending on the case that you are working here, when this is going to be used, because you have to make that change of a state. You see, you have to make that change of a state. And after having solved this next state situation, after having solved this next state calculation, you are going to reset this flag that way. So from now on, you see, this variable start flag or clock flag, the one that you've been using to make this transition, is reset. And it is kept that way until you have another interruption. That is the mechanism that we will use once and again, all these examples. All right? And you can inspect that as well from this perspective, and because this is going to give you an insight on that. Look at this. Perhaps it is better at this level of definition here. It's all right. You see, what is the meaning of of a level sensitive signal. Why we talk about reading and why we talk about detecting edges? Well, because there are these two kinds of signals. Sometimes we are interested in reading or pulling the value of a given input, for example, the count enable, because if it's detected to be 1, we will go advancing from 1 to 2, from 2 to 3, and etc. And there is sometimes where you like to detect an event, a specific event. For example, that the push button has gone from high to low, just this time. So you like to detect this time. And to do that, you see, to detect this falling edge, you need the interrupt mechanism. So, you know, we have this difference stated in the name of the variables. If the variable that you like to read or pull exists and you need it, is going to be named like this: bar, for example, bar count enable, only bar, okay? Only bar. But if what you are is detecting an edge, okay, the variable has another name. The variable has this name, var star flag, okay? That way. The flag means in some way that we are talking about a signal that is sensitive to the falling or the rising edge of a, or you know, later on is going to be the overflow of a counter or the bit that indicates that you are receiving a data from the serial port, and etc. etc. So some specific event that happened at a given time, for example at time t1. Okay, in this way it is possible as well from the same signal, you see, if you have a signal like this, start, it is very possible, if you like, to configure the system so that you can detect both edges. There is no problem on this, okay? There is no problem. If you like, you can detect the falling edge, and then you can reconfigure the input so that from now on, you see, is sensitive to the rising edge, and later on it's again sensitive to the falling edge. You can do that by software. In this way you can organize different flag signals, for example the start flag and the start to flag, if this is what you have in mind, okay? And there are many applications where this kind of thing is necessary, and I insist on this. These variables are fundamental because they are used to switch from one state to the next in the state diagram of the finite state machine. And that is what happens. Some conditions, some state transitions do not happen unless you have, for example, a variable that you read set and a variable that is setting the flag set. So if this is what you need, this has to be detected and saved this time, you see, in memory. So you can use these two memory variables to go and make that kind of change of a state. That is the point. And naturally, perhaps there is something else to say here, is that when this flag is used, you see, when this flag is used, because it is used in the main program, when this flag is used, for example, here it can be explained like perhaps better. Okay, when this flag is used here, because it is used for changing the current state. So here, the next thing that you have to do is to clear the flag in the main program, right? So that you can be interrupted again, all right? That is the point. It takes time to explain that, but it's because it's all the time the same way. It is worth to pay attention to this description. Okay? And finally, if you see that interrupt service routine from the perspective of the main program, well, it's not that difficult as well. Look at this. The computer is executing, as you know, the program memory. Here is where you have the main loop recorded in instructions in assembly, you may say so, right? Machine code but you may very well talk about instructions in assembly language. The C code has been compiled and transferred to the main program of the program memory by means of, assembly instructions. And every instruction, for example, takes 4 clocks or 8 clocks to be executed, depending on the kind of instruction. So this is what the program is going to do. You see, you have a register that is named program counter in all the computers. So the program counter is pointing the instruction that is executed now. And then it goes to the next instruction, or perhaps because it's a subroutine, it goes down to execute another instruction, and then it goes up this way. Okay, you have to play with the machine plays with the program counter and as well the stack pointer to go jumping from one function to the next. But in some way you can simplify this situation, explaining that what you've got is a section of program that is the section of the memory, the program memory, the flash. Okay, the flash memory or the EEPROM memory in some way is electrically erasable because you can reload another program later on in the same program memory. So you have a section of this memory that is occupied by the main loop. All right. And then naturally you are not going to occupy all the program memory. So there are sections of the program memory that are not used. And the point is that somewhere else, you see, before the main loop or after the main loop, what the program or the compiler says is that it is devoting some extra memory, program memory space to save the interrupt service routine. So you see, once the main loop, because it's on execution this way, when it finishes, it goes back to the beginning, to the first instruction of this main loop again. Set aside is as well the init system, but after the init system, the system jump to the while one structure and is kept this way. Okay, but you know, the same way that the init system is set aside, you have set aside the interrupt service routine. So when the interrupt happens in between the main instructions that you are executing in the main loop, for example, at this time T1, when you are detecting the start button flag, this is the start button edge that you like to detect, you know, what is happening indeed is that the program counter is loaded with the value of the first instruction in the interrupt service routine to execute. And so from now on, the program executes these instructions, and in the end, when it finishes, it goes back to the next instruction in the loop. That is the way it works in some words. Okay, you now understand that a lot better if you take a book and you read it correctly. That is more or less what is happening here. Okay, the general ideas. Okay, so this picture is like that. It allows you to understand as well another very, very important concept. Look at this. Look at this, because this is something that is generating a lot of complications if you don't understand that correctly. Let me explain that to you to finish this slide. Okay, and it is about the reading time. You have the read input function established in the main loop. So it is going to happen that every time that you are executing the loop, you see, whatever the way you like to see, every time that you are executing the loop, you read the inputs. But what? Well, the time in which you are reading the inputs is going to change. It is going to be repeated, but sometimes it is a shorter time and sometimes is a larger time. You cannot avoid that pattern. You see, it's not like having a clock. Why? Because you see, this is software. This is not something like a 3-level of gate circuit that is what we had in the chapter 2 when we did that using hardware. This time you are using software. And you know, the state logic and the output logic and the write outputs has different instructions. For example, you have ifs and cases and switches and many more instructions of this kind that allows you to go through the software from one way or another, making that this situation very likely possible. You see that the time in which you go back to the beginning of the loop is different, because that depends on the circuit of instructions that you are following through the main loop. Sometimes you will go faster and sometimes you will go slower, because now you have to write some LEDs, or you have to send information to another place, or you have to print a message on the screen, and that takes a longer time. So you see, for example, this time takes longer because you have an operation to carry on, and then it is shorter because there is nothing to do, so you can read faster. You see, that is what you've got when reading, when pulling. You pull the value, but you see, the pulling of this kind of inputs happens when it is. You cannot avoid that situation of having shorter times and larger times. This is something very important to take into account, because if you go like this, you see, and by any chance you like to detect an event of the signal like this, you see, there is no way you cannot detect that transition. You can read before that this was a 0, and later on, perhaps because you are again in read inputs, you can read that now is 1. But in any way, there is no way to detect that situation, that time, I don't know, t equal t3, where you have this edge, if this is what you want, right? Another thing is that you are not interested in that transition, which is the case many times. But if by any chance you like to detect this transition, reading inputs, it's impossible, okay? Because you have to be executing the instructions to read. You know what it works. You read all the pin ports, you clean, and then you apply a mask, and then perhaps you shift the bits to get the right variables to be used later by the machine. So to do that, you have to be executing these instructions, and that is only possible when you are just executing these instructions in the read input, not any other time. So if the signal changes in between, you cannot detect that edge in any way reading, unless that you can imagine that goes at very high speed, but that is a problem. You cannot, perhaps there is no way to read that fast, okay? So what you can do to detect, okay, there is that solution naturally. If what you like is to go and detect an edge, you have this mechanism, okay? You have this, if you like to detect an edge, let me insist on this, you can do that by means of interrupts. And this is what we are going to do. Use the interrupts to set a flag so that we can jump to the interrupt service routine. And that is in some way a long explanation of this picture, but is necessary, all right, to clarify the situation. So the interrupt logic works because you have this kind of circuit, a very simple circuit. In some way, we will talk about that many more times, because we may like later to be interrupted by the timer or another peripheral. But you see, in some way, it's not that complicated. You have the flag. This is the hardware circuit that is here, that is the one that will generate a hardware flag. Okay, basically the output of a flip-flop. So the flip-flop will be set a 1, and this one has a name. For example, the interrupt 0 flag. So this flag is like this, a 1. And if you enable, you see, if you enable this interrupt, this one that is set when it has happened, this one is considered. And because you have an OR now, this one goes to the final AND. And if you allow the general interrupt enable, if you allow these interrupts to happen, you can interrupt the CPU. That is the way it works. So you see, in some way, every single peripheral, whatever it is, the EEPROM or the analog to digital converter or the transmitter system or the comparator, because there is a detection of two different signals, or the timer 2 or the timer 1, doesn't matter. In some way, every peripheral, like the timer 0 or like this one that we are using in this example, the external interrupt, okay, the int 0 and the int 1 and the int 2, this is the port B0, this is the port B1, and this is the port B2. So if you are configuring these pins in this port to be used as, you know, interrupts, what is going to happen is that you have here the flag, the possibility that if you are programming the falling edge in the int 0 when this event happens, so you have the int 0 interrupt flag set to 1 automatically by the hardware of the microprocessor, right? And if you allow with the one in the enable interrupt, this one is finally interrupting the system. This is the mechanism that we will use, right? And you know that this is this hardware related to the interrupts is related to the ports. You see, for example, this is the general configuration, as you know, of a port. And you know, in a port you can read and you can write depending on the trees. Okay, this is what you can do. You can use the trees value, okay, to convert this port, because you have the 3 states. So this is the pin. So if you like, you can convert that into an output. So the data that is present in the internal data bus can be conveyed to the output this way. Or otherwise, if you are programming the trees with a 1, it happens that this one, you see, is blocking this gate. So this gate is not going to be active because it has a bubble here. You see it's 0. So the output direction is not going to be taken into account, but the input direction instead. So you see, the data from the pin is going to be captured and transferred when you read the port, you see, transferred to the data bus. This is the way it works, okay? In general, for every single port pin. But if this pin is, you know, the RB0, for example, that has this name, in0, if this port is that one, you can also configure the pin as input, but you know, you can use this path here, you see? You can convey the signal not only for reading as usual. If you like, you can read this value, but you see, there is this special gate that makes this signal connected to the interrupt logic, okay? And the final flip-flop that is for setting the interrupt 0 flag, the one that in the end is able to interrupt by this way, you see, by this hardware way, the main program, okay? So this is for this example and for the others, for any other example that you can imagine based on interrupts, which are almost all of them, because, you know, this is what we have in mind. So very well. Then there is the hardware situation. Well, the hardware is, you know, here we can go faster because this is once again the same idea of connecting pins, okay? Some pins can be connected to conventional ports, whatever they are, the port 7, the port D, bit 6, bit 7, the port A, bit 2, bit 1, you can make that this way. For example, another port pin, the port C bit 2 is the one that is the end of transmission in this example. So you can do that for your example. Well, your example is not that one. You see, your example is the counter. So you have to find this hardware thing for the example that we are studying here, right? And this example that we are studying is this one. Yeah, sorry. This is the hardware, okay? The basic one-digit BCD counter. So here is where you can make, kind of study this to see what happens, okay? The power supply, some pins are used as the BCD code outputs. There is the crystal, there is the clear direct circuit, always the same. And then look at this. This signal is special, and this one is the one that you will read or pull anytime you find it in the main program, and this one is the special one, okay? This is the clock, because here what you like to do is to detect, for example, the rising edge. This time is the time that you like to detect to make it possible the counter go advancing as usual, okay, on the rising edge of the signal. So this is the hardware that you may very well later on capture in Proteus, so you can go and later associate the code to this hardware. And then there is the software. You see, you can go advancing here. Now is the picture 5. Then is the picture 6 that explain you this idea of the adaptation of the finite state machine. Okay, the many input X now sometimes are level sensitive and sometimes are edge sensitive. Okay, so all the outputs are generated by the CC2 logic, the output logic, and the next state to go, you see, the current state is generated by the state logic. And there is only one remark, because it's good to remember that, you see. It's good to remember that now the current state is a RAM memory position. Okay? It's a RAM memory variable, current state. So this variable is used when you go back, because it's a loop, right? When you go back to the state logic and output logic, if this variable has changed, it is taken into account to calculate other outputs and other possible next states to go. That way, you see? So when we here say S plus, the next state to go in the future, the plus means, you see, this plus means that this current state is updated after each software loop, not like we had in chapter 2 after very single clock, but now after each software loop. That is what happens. So you see, in some way the synchronicity has disappeared here. It's not that way anymore. Perhaps you can make that quite synchronous to external clock, programming interrupts and the like, you see, making the system jump. But you know, that is different. That is not the classic synchronicity that was defined in chapter 2 to update the state register. Because you see, this is a RAM memory position, and if it has to change, it's because you are executing again this function when it happens that you are executing this function. All right. So that way. Then the same picture. All right. And then, well, with all the details explained again. You see, these details are remarked once and again, perhaps, because this is the point. And then you have again this picture that is already discussed in the general explanation. Okay, the idea that yes, it perhaps a software thing that you've got here, but you know, it is a hardware platform, a microprocessor platform that allows you to convert pins into variables and edges. You know, you can convert both. You see, look at this. You can convert pin levels into variables and pin edges into flags. So you have both the flags and the variables to make decisions to where to go next by means of this current state variable. And this is cyclically executed by the main loop. And the same way, if you have the variables that are calculated by the output logic, you can transfer the variables into a given set of pins. All right, that's the way. And because it's a computer, you have to take into account as well that you have an oscillator system, for example, running by means of an external clock, and the master clear circuit that when you press the button reset, the system initializes, going to the first memory position again. All right, that way. As usual, so there is no point in repeating that anymore. You see, that is more or less what it takes to explain that thing. So then, as usual, you have to be aware of the many variables that you have in the memory. That is important picture, because these variables are the ones to be used in the programming of the next state and the output state logic. So you have to be aware of the many variables to be used. And our strategy here, as you know from P9, is to do this idea. Even if you are talking about a single bit, now you have a variable that is a full char. Yes, with many zeros that are not used. Okay, but this is not a problem. You have a bit here. The bit 0 of this variable is the level that you've been reading. And the current state, for example, is just another variable. This time, for example, a char variable that contains, for example, a capital letter. Okay, A, B, C. So in this way, a label like state 7 can be saved in the internal memory. You see, this label can be saved, yes, as a binary code, or yes, as a one-hot code, as a gray code, as we did in chapter 2. Yeah, that was right there, but now let's make it easy. This label is saved as this ASCII capital letter, I don't know, key, okay? To make it easy. So the content of the current state variable is just the ASCII code of some letters to be easy identified then when you run the watch window. All right, and the same with the outputs. If it happens that you have a BCD one-digit representation, a number from 0 up to 9, this is in binary 4-bit, and the 4-bit can be saved very well like this with other 4 leading zeros for keeping this variable in a single char, and that way all the time. Okay, so perhaps this explanation here is longer, but it's going to be the same and a lot faster for other examples. So then what? Then goes the idea of inventing function by function, because you see here you have a recall, you have very well explained what is necessary. You have to spend some time designing the init system, okay? And then you have to spend some time designing the read inputs, the write outputs, and the associated logic to interrupt service routine. And finally, you have to solve as well the truth table of the output logic and a state logic. So this is what goes now. For example, the configuration of the bits in the trees register, okay? And then the possibility to read the inputs, so you have to invent a flowchart and to write outputs the same way that you did in P9. So this is not explained now because it's the same thing. You see, read all the ports, clean the bits of no interest, and mask the bits of interest, and then shift the bits so that you are composing the right and the correct var variable of your interest. And the same thing with write output. Remember, first of all, we read all the port to save the information of the bits of no interest. And then we, at the same time, clean the bits that are rewritten, okay, rewritten. And then we shift every single bit to the right port position, and then we write all the bits of the port. We do that when writing. Okay, and for example, the interrupt service routine is going to look like this. You see, very simple, because it has to take not a lot of time, some microseconds, a very few number of instructions. So if by any chance you see there has been an interrupt, so very well, what you have to do is to ask, the interrupt is due to the flag of the external interrupt, because remember that is the only possible situation that you are supposing now here. You see, this is the int 0, this is the bit 0 in the port B, so this is what you like to detect, for example, a falling edge. This is the reason why I've got this jump to the interrupt service routine. That's a fundamental question, because if this is not the reason, something wrong had happened and the system has got out of control, because the system cannot reach the interrupt service routine unless it is interrupted by one of the sources that you have programmed. Okay, you see, remember that you can program any single interruption source. For example, if this situation has happened, is because in the int or anywhere in the code you have decided to set this flag, int 0 interrupt enable 1. You did that in the code, for example, in the init system. So now the program is executing this instruction. So you may ask if this is the reason, right? And then naturally, if yes, you simply say the flag high. That's it. Okay, and another important thing that has to be remarked, but you know what I mean. Okay, another important thing is that one, you see? Exactly. Okay, you set the flag, set the software flag high, and at the same time, or later on, just an instruction later, you simply delete the flag, the hardware flag, so that the machine can be interrupted again. So you have detected now this flag, this edge, and later on in time, who knows when, there is another falling edge to be detected. Okay, right, so now you are detecting this falling edge, and this is why you are now in this interrupt service routine, executing these few instructions to set the software flag and to reset the hardware flag. So after this detection, after having set something like bar clock flag equal 1, you have to say, you see, immediately after that time, int 0 interrupt flag equals 0, because in this way later on, you see, many minutes later perhaps, or some micro or milliseconds later, there is another external flag of the same kind. So here you see the int 0 interrupt flag is going to be set again, and so you will be able to jump again to the same function to set again the bar clock flag to 1 to be used in the main program, for example, by the state logic function. That is the way it works. All right. So, you know, one that the detail on the interrupt service routine is clear, well, it's about programming it, you know, these very few instructions. And then you have to continue programming something that you know very well from chapter 2 already, which is the truth table of this combinational circuit, the state logic. But pay attention now that you have, instead of bits and, you know, bits, I mean voltages or pins, what you've got are a set of variables. So containable is value containable. The clock this time is a clock flag, and you have a current state input value. So in this way, you see, you have this typical table that you know very well, and it is simply the set of inputs and then the calculation from the set of inputs, the calculation of the next state to go. So you see current state plus, that is the way. So you are here processing all the loops and all the arrows in the same way you did in chapter 2. So you can go state by state, you see, programming all the arrows that you've got here. That is the situation of the state logic. Simple, right? Okay. So the same with, once the truth table is clear, what goes next is the translation of the table into a flowchart, because here we will take advantage of the labels and the variable names and what? Well, the flexibility of the ifs and elses and switch and case instructions, because that is the easiest way to implement that. Instead of talking about, max terms and min terms and a hard circuit, we better interpret that in this behavioral way. That is the huge advantage, something that we already discovered before in chapter 2. You see, you have, or in chapter 1 as well, some combinational circuits can be described, for all of them, if you like, can be described very well in this behavioral interpretation. And what is the point of doing that? Well, because this rhomboid is directly translated to an if, and this multiple answer question, which is the current state, case state 0, case state 1, this is very well translated by means of a switch into a C instruction. So that is the great advantage. So you see, from the flowchart, you get what you want, which is the C code of the function. You see, it's going to speed up the translation of this flowchart into C that way. All right. And finally, you have to do the same for the output logic, whatever it is. In many circuits, this logic is a lot simpler than the state logic. Okay, you have, for example, current state variable and value containable, because this is a counter, and the BCD code is just a translation. You see, if it happens at the state 8, the only thing that you have to say is that you like to get 0, 0, 0, 0, 1, 0, 0, 0. In where? Well, in the bar BCD code. Okay, this is where you like to save exactly this value, because this is an 8 in BCD, and then you have to solve the value TC10, and perhaps you need to do that using the value containable as well. For example, if you are at the state 9 and value containable happens to be 1, if both conditions are met, you see, you like to get a 1 and 0 otherwise. So this is the typical function that has a single minterm, if you think as in chapter 1. But you do that all in C code. Okay? So that's the end of the planning. You see, it's quite a long planning. It takes time. This 1 hour is like that, but the point is that it's like that for all the projects. So the next project that has to be explained doesn't take that much time, because it just slight differences, perhaps 2 interrupts instead of 1, perhaps an int variable instead of a char variable, but the main idea and the main conception is exactly the same. So once you've got this from a class or from a lab session or from a recording, you got it all. Okay, you have everything in your mind to understand what goes next, and naturally what goes next is that simple. Okay, well, I've missed here the same idea of translating the table into a flowchart, so because the flowchart is the same time the same idea as the code. So what goes next is simply to think about implementing this circuit in a given folder location, and go into the development section, and that is where you have to use the tools, the proper tools. And here the proper tools are the Proteus simulator, because it allows you to use microcontrollers and electrical circuits all at the same time along with the program. So here in the development section you have the hardware circuit, that is the translation of the previous picture, and you have as well the software file, that is the translation of all these flowcharts that we've been studying before in sheets of paper, right? So this is what goes next, and this may be continued in this same video, using these tools and establishing two windows, one window for the hardware and another window for the software, as we did in P9. So from now on, it's not that different from the other recordings that you already had here in previous sessions. Okay, so let's go to the practical thing. This is the counter BCD 1 digit, the developing idea. This is what we've been explaining that long, the meaning of every single picture and diagram and flowchart, and this is what is left now, the developing and the testing, and we will do that together. So let's save the hardware, let's save the link as, this computer, the unit LCSD, this semester, this is P10. So the counter BCD 1 digit hardware file, let's save it here in this folder, and the same with the software. Save the link as in the same place. So now what you've got is this P10 folder that has, the two files of interest, the hardware in one hand and the software in the other. So now it's time for inspecting the hardware that you've been downloading from the internet. Let's see how it's going to look like in this Proteus environment. So it is looking like this, you see. So you have the circuit, and then you can go to the child sheet, and here you have the clock and the computer, the PIC 18F4520 connected as expected from the sketches, you see. And pay attention to this line here. The clock happens to be the RB0, the int 0 this time, okay? And for example, the count enable is just the next line, the RB1 in the same port. Well, doesn't matter. This is the connection. So now what is required here, if you go to edit properties, you see you have the processor clock frequency and this file that is not yet here, you see. This is what you have to find now, or generate the COF file to be associated to this hardware so that you can simulate this circuit. So now it's time for going to the top and setting aside this hardware window, because if you click now run, you have the error because the program is not here naturally. So it's trying to run. You see the simulation, it takes time, but in the end it's not going to run because the program, the COF or the HEX is not here yet. Okay. Okay, you've got this error. The program property is not specified yet for this chip U2. So very well, let's do that. Okay, so let's set aside this window, and now it's time for finding the MPLAB X so that we can compile the C code. So let's clean everything. So let's get here a blank workspace for in this integrated development environment, you see. And now it's time for new project, as it's a standalone project, and the PIC 18F4520 is the chip of interest this time. And the tool, it doesn't matter very much. We can pick up the ICD3, so you can say next. And now the compiler tool chain, well, the hardware is not necessary because we will solve that lab assignment in the simulator itself. So now it's time for selecting the XE8, that one. Okay, so you say next, and now it's time for finding what you want, which is the program folder or the project folder. And this is P10, and this is the project folder. It should be here. Why the project folder is not here? So something is wrong, you see. So let's cancel this destination do not exist. So we have gone that too fast. So let's take it easy. Let's go to the hardware and let's switch off the hardware, exit the application. Yes, let's save it. And let's go back and review the folder section. You see, this is the P10, but the P10 do not contain the folder of interest. So let's make that clear, okay? Let's make that new folder. This is the project name. So let's place it all down there. And now this is the project location, and here is where you have to have both files, the C and the hardware. So these ones which are generated now as backups can be deleted, no problem. And if you like, you can start the Proteus now again, no problem. So now everything is in place. You see, when doing that, you have to review what you are doing in case you get some mistake. And that is an important error, because then the things do not work properly. And besides, here in this project, later on, you like to add another exercise, another project of the similar kind, another finite state machine in P10. So every finite state machine that you are solving has to be in its right folder. Okay, so let's continue now, because we can start that. This is the XE8. So now if we browse for the right location, CSD, this course, P10, and that now is the right location. So you can copy the name now, Control-C, you can open that location, and the project name is as usual, the same name, counter BCD 1 digit _PRJ. And then you see the machine generates another folder for everything that is related to this project of compilation project. You say nothing else, and you say finish. You click this button, and now you have an empty space, but already customized for your micro, okay, for your microcontroller. But it still has 0. You see, you have 0 files here. Okay, so now it's your turn to go and add a source file, because this is what you have as an existing item. You see the great advantage of this, starting from a well-known exercise that is completely solved. You don't have to worry about now the syntax of the C language, because you can pick up this language, this file that exists, and this time is not here, but just one level up. Okay, here, that one, you can copy it, and now the source file is just what you've got, and you can open it like that, click, and this is the file that it is exactly as described in the previous explanations, okay? But in C, you know that we got that exactly in VHDL. So now you have the same thing in C. And that is very good, because you can go comparing. Because, you know, engineering is about having many solutions, if possible, more than one, and be able to select which one is better. So here you have the counter, 1 digit, BCD from the computer perspective. So here you have the definitions of the prototype functions, all the variables that you know very well. And what else? The main loop, and then the definition of every single function. State logic like this, you see, you do nothing, you read inputs and you do nothing unless there is a flag from the clock. You see, this is in some way the method that you have to synchronize your circuit to this external clock, okay? If there is a clock, and then you can switch depending on the current state to do one thing or the other, to keep the same state or to go to the next. That's simple and that easy to the end, okay? So look at this. If you are the number 9 and the variable, the containable is high, you see, is 1, has been read to be 1, then you go to the next state, which is 0. Okay? Something like this. Because if this is not possible, what you do is to keep the same state. Okay? So the loops are in some way implicit in this description in C. And you see, that is what I like you to comment now. You've been using, by means of this if, the variable clock flag, and you have executed all this switch structure. And when you have gone out of this switch structure, what you do here is this fundamental idea. You clean, you reset the flag related to the clock, so it can be set again in the interrupt service routine down there, you see? So the interrupt service routine, when executed, is the one that sets the software flag and, as we explained before, cleans the hardware flag. So by means of another edge detection, you can go back here to trigger another software flag, variable clock flag this way, and be able to execute again, you see, another time what is inside this if, this switch that allows you to switch from one, to change from one state to the next. And well, the same with the output logic, but this time easier. You see, you have a switch for establishing the output value. And then perhaps here you have an equation written in C, a logic equation. You see, you have now the logic operator. Look at this, 2 ampersands. This is the logic operator, not the bitwise operator that we used in read inputs. This time, this is the classical AND. If this is true and that is true, you do that thing of setting the variable bar tc10 equal 1, because if this is false, you see, if this AND do not happen as so, you keep this variable low. And then you finalize the main loop, you see, this way, writing the outputs. And well, the program is kept in this loop. And perhaps the only thing that now is here to explain is the read input. But this time is that simple. You see, you read all the port and you mask the bit of interest. You see the RB1, and then you shift it 1 bit to the right to be able to construct the variable of your interest, the var containable, to be used, as you see, in the main program and in the main loop and in this switch structure. And the same thing, it has to be solved for write outputs. So here you read, you mask the bits of no interest, at the same time you clean the bit of that is going to be rewritten, and you do that final writing of the port with this bar data, this bar buffer, you see, and the variable tc10, but you see moved, shifted 2 bits to the left, so that now this goes straight to the port B, bit 2. Okay, this is where you have decided to place this pin, the tc10 pin. And the same with the variable that is called, you see, this time you are masking 4 bits, because what you like is to write exactly the BCD code in the same port D from pin 7 down to pin 4. All right, and init system looks the same all the time, so you have to keep as they are the pragmas. You see, this is the initial configuration of the microcontroller, and this is not used in the very much, well, this has a meaning when you download this hex to the prototyping board. So here you are configuring all the bits of the microprocessor, and you do that in one way that is not interfering with the simulator in any way. So the initialization starts here, as indicated with this comment. Okay, you simply write the right values in the trees. Okay, for example, the trees D means that these port 7 down to 4 are set as outputs, and here you see the 3 pins. 0, 1, 1 means that the RB2 is the output TC10, and the RB1 is the input count enable, and the RB0 is the input external clock. This way. And then there is something fundamental here that you don't have to forget, because here you see you like to receive, you like to be sensitive to interrupts. So this is the point. You have to program specifically, well, this is for programming the edge. You see, int enable edge, you see, interrupt edge. Here is where you are deciding to be sensitive to the falling edge or the rising edge. You see the right value from the datasheet of the PIC microprocessor. As 0, I guess it's sensitive to the falling edge, but you know, it's not important. Whatever. Some problems are based on falling edge detections, and some problem are related to rising edge detection. That has importance because in some way, well, this is related to the hardware circuit in the way you have connected the push button when you are using push buttons. Okay? When you click, you generate a falling edge. This is the situation. But when you click, you generate a rising edge. You like to save here a 1. That's not important. And then what is important indeed is the interrupt 0 enable. This has to be 1 to allow the interrupt logic to go to the end and be able, by means of this next interrupt, general interrupt enable 1, to be able, in this way, you see, you can go out of the main loop because of the reason that the external interrupt 0 has been detected. That is the point. Okay, and well, that is a good idea to initialize the clock flag 0 as well. So when everything is in place and more or less everything is understood, you see, you don't have to understand that just now. You can do that through the many exercises, because many things here are going to be common to all the projects, especially the software organization and everything, almost everything else. So once the code is written, perhaps, let me pay attention to the include. You know, the include exe, this header file contains all the other files. So you can go to the tree, you see, you can go to the last definition, you see, you have here a single file project for convenience, but you know, your file includes many other files with all the definitions associated to this microprocessor. And that's the great advantage of using this integrated developing environment that keeps it all just that practical. Okay, just a single include for you to be able to use any kind of definition like port A or interrupt enable. You can use these kind of labels in capitals because they are defined in these include files. So very well, when everything is clear, you better go and select the properties, the right ones. Okay, so go to the properties, you see, and now go to the global options, because we have the idea of using the C standard 90, and the COF output file, because that one is the one that connects to the Proteus simulation environment. So let's set these two global options this way. Let's apply that conditions and let's say okay. And now it's time for what? Well, the sweeper and the hammer. You see, you can clean and build the main project. You can clean, not now because the project is going to be compiled for the first time, but when you do that once and again, it's a good idea to clean the previous files generated before in another compilation process before. In this way, you always have clean files. So you see, in the end, you get 0 errors, and that is the important thing. This means that you can go now and run that thing. And here you have the memory summary. As you see, it's a computer. So this teeny program is using 1.6% of the memory space capacity for saving programs. And you know, it is using 8 bytes of data, right? And you can count them very well. The 5 or 6 or 7 or 8 that you've been declared as a static char or a static ins or buffers that you are using for saving partial results. So you see 0.5%. This is why it's not that important to waste some bits, filling in some bits with zeros, you see. That is the point, because there you have plenty of memory to be used in any one of these simple applications. Okay, besides, we are not pretending to optimize the program. The only thing that we have in mind now is to run it and be sure that it works as expected. Okay, if you pay for a compiler, a professional compiler, you will see that this space is reduced a lot. You see, this is what the compiler, the professional compiler does, you see, to reduce the program space a lot and make the program more efficient. And this means that the same loop that you have here is going to be executed a lot faster, because it can be optimized many more than it is now in this free edition of the compiler. But in the end, what you like from this program now is to set the windows aside and go back to the Proteus, go back to the child sheet, you know, and now because the project is here finished, compiled, you can edit the properties and you can find the program file, okay? And the same way that you are setting the clock processor, you can just go and fetch, you see here, P10 counter. Now you have this project folder. You can go to distribution and default and production, and here it is the COF solved just now. Okay, you say so. And you know, we take the COF because we like to go step by step and watching variables. If you go and download the code to the platform, the real platform, you better take the HEX. Oh, this is the one that the HEX is the one that the programmer will take to download the real executable file to the platform, to the microchip platform. So we do that and we say okay right now, and we go to the top, and now the program is going to work. Let's suppose so, right? Everything is in place, everything is all right. So you have now the platform, the hardware platform, and here you may say run, okay? This way. So now the program is running. Okay, you see? A simple counter that is counting up. Okay, guys? And you can click buttons this way, you see? Now you are generating edges. It is that clear. You see, you have a level high now. You see that thing? You have a level high. Okay. You have a level high all the time in this clock input. So nothing happens. The system is stuck here. But when you generate a falling edge, this falling edge is detected. So the project can go to the next state. Okay, that way. And now you are at the state 9. And well, the system is reading a 1 in the count enable. And this means that it can go on. But if you switch it off this way, you see you have still the same state 9, but the TC10 goes slow as expected from the, from the timing diagram. You know that. This is what you've been programming. Okay? So very well, you let the system go counting and you can continue applying here pulses. By hand, okay, you can reset that anytime that you like. For example, the counter at this stage, you can click and now immediately it goes to 0 and you can go counting up this way, or you can go counting up automatically because you are connecting now, you are generating the falling edges by means of this external oscillator. You can do that again. You can stop, you see, no problem. You can stop that. Okay, you can stop and you can change the frequency of the counter, for example, 20 Hz instead of 2 Hz. Okay, if you do that, the counter is going to run a lot faster that way. The same way, but faster because there are a lot more rising edges. So very well, this is the developing section and this is, the starting of the testing, and this time, well, fortunately everything works, but that's not the case. Most of the time when you try to modify the program, something goes wrong, okay? Okay, for example, I can provoke that situation very well. Here, I can go back to my software and I can recompile that. For example, provoking a mistake. For example, here, I don't know. Let me change something. For example, the bit, the initialization bit that tells that the count enable, I guess, for example, this bit 1 here, remember that, okay? Let's provoke a mistake. Control C, Control V. This is now the right instruction, and this is the instruction that is expressly solved wrongly. You see, you are writing a 0 in the trees B, that is the RB1, and in RB1 is where you are deciding this direction of the count enable. So you see the count enable signal is not going to work now because cannot be read. Okay? So look at this. You have now this instruction. It is an error, so you can clean. That is the great advantage. You have the two windows at the same time working together. You can recompile now. You are cleaning the previous vector, the previous project, and generating a new one with 0 errors. You did nothing illegal, but the only thing is that it's not working now. Let's check that. Let's go back to the hardware. Let's stop the previous simulation, and when you start the new one, you see, okay, you have the clear direct and the machine, it is not working. You see, the machine is not working because you see the count enable maybe not set. You see, so you say, what is happening here? The system is running. You see, you can go step by step. You can see the variables and you like to be sure that the system is running. Effectively, the system is running, is engaged in the main loop, executing state logic and output logic continuously. You have the variables, you see? But what you are realizing here, perhaps using the watch window, you see, you can go to the book and add a watch window and drag to this watch window, for example, the variable of interest, the very important one, the current state, okay, that is signaling the state num0, value A. This is the value that is saved here. And then the other one, the bar count enable, this one, for example, you see it is kept to 0. So now you can run, okay, you can run in a continuous way, so you can spy the circuit. Because it looks like that the LEDs are not working for you now, you see. And so the system is executed, you see, and this signal is not detected because it's an error in the code. Everything is all right, but you did something wrong once when you type in instructions in C, okay? So there is no way, it doesn't work. So let me see if this is because, no, it is not working because of this signal is not detected. You see, you can do what you want, but you run and nothing happens. You are stuck at this state, you see? Okay. the system is not sensitive to this edge. So you have a problem. So the way to solve the problem naturally is to stop the simulations and go back to the software section and review what you did, and then is when you see, aha, I did that wrong. Okay, this is the right instruction. So you changes the things here in the code, and here is when now you are really programming the count enable as an input. And so now, yes, it is possible to read this input. So what you do now is that idea of clean the previous edition and recompile. You see, in 2 seconds, you do that again. So now you are that lucky that you have another edition of the COF, but the COF is already attached to the circuit. So that is an advantage for you, because the only thing that you have to do is to stop simulations. You see, let's stop the simulations and let's run again. And now you can see that the system is working well. You see, you have the current state that is moving, every clock detected, and you see that the bar count enable is rightly detected as a 1. You see bar count enable active high as a variable, so is 1, so you can go from one state to the next. And here you have a 0, so you keep the state 9 like this, you see, or the state whatever it is in which you have set. So you see, you are saving the state 2 all the time. Even if you have rising edges, you go nowhere. That's the way it works. Okay, and finally, well, you can print that kind of thing, and you can go step by step if you like, stepping over or stepping into the functions. You see, you can use these 2 important tools, and you can answer as well the important questions here that are asked you every time. So we are running now an infinite loop. So the question is that clear. How long does it take to execute a turn around the main loop? So now you can solve that establishing here, for example, anywhere in the main loop. This is inside the main loop. You see, inside the while one, you click and you are setting here a breakpoint. So now when you run, you see the machine stops all the time at this instruction. You see, so you have here the information. You see, you have a digital breakpoint at 40. You see the point? You have a digital breakpoint at time 40:53 and 45:03. You see, the system is advancing slowly now in time, you see, but you have a very important information down there. You see, 83 microseconds elapsed. So this is the time that takes to execute the main loop, 83 microseconds, because probably you have here some instructions, as you know. You see, you can see some of them. You see, you are executing. This is where the breakpoint is. You see the machine executes this call, this bit test, and this branch. So you see, so the machine is executing instructions in assembly. So every instruction of this kind takes 4 or 8 clocks. So in the end, a clock is 4 megahertz, the oscillator. So 4 clocks is 1 microsecond. So you have several instructions here, and then you have several more instructions inside the if. You see, if you are moving around the if, you look at this, you have a lot of instructions to write and to do the every idea that you've got here defined in C. Okay, so in the end, you see, if you go from one breakpoint to the next, it takes 83 microseconds. So if you think about the number of loops per second that the system is running, you only have to go and take your calculator and invent and calculate that. 83 microseconds. It's exactly 12,000 times 12,000 times per second. So this is the speed in which the loop is running now, okay? And you know that you can do that loop larger, introducing more instructions, or shorter, optimizing the code, or whatever. And you know that you can execute simply this loop 4 times faster, going to the computer, stopping the simulation, going to the computer and setting not the picture, right? The picture doesn't matter because it's a simulator. So the value that has interest here is the clock. So if now the clock is instead of 16 megahertz, you know, you have to execute the same number of instructions, right? But 4 times faster. So if you go to the top now, because you have changed that oscillator, it's like soldering another clock for this computer in the board. So when you run now, you see, you happen to have the same breakpoint in the same place, but now you see the time elapsed is only 19.25, exactly 83 divided by 4, okay? Or something like that, okay? Is that right? So this is the time elapsed. A lot faster. So if this is what it takes, 19.25 microseconds, so it means that you see this time, because you have a faster clock, this main loop is executed 52,000 times per second. Well, not bad, you see, but you know, this is a microcontroller, and this kind of timing, you see, 52,000 times, you see, let's say 19 this time, because you have a higher frequency for the oscillator, 19 microseconds. Okay, you have to realize that that is okay for many applications probably, but this is not that good if you think on the same circuit solved using pure hardware. Remember, 19.2 microseconds is nothing but 19,000 nanoseconds. And remember that when we did that circuit in chapter 2, we could solve it very well in 5 or 10 nanoseconds. That was the idea there, you see? Just, you know, a delay from the clock to the output, and then a delay associated to the CC1 and CC2. Let's say 3 levels of gates if you have a complex PLD. And that means that probably in 10 nanoseconds, you can run the finite state machine. So that is going to give you a very different frequency. You see here, one thing is 50,000, you see 50,000 times per second, you can see, well, 50,000 Hertz. And another thing is not 50 kilohertz, but you know, 100 or 200 megahertz. You see, you have several orders of magnitude here of difference in this specific characteristic. Okay, this future, the computation speed, it's a lot faster when you talk of the circuit solved in hardware. Okay, but if you like, you have here the possibility to solve the same coder now in software, and that is well, perhaps not the speed, but it is very useful for many applications, and it has a lot of advantages as well, this kind of method. Okay, and one of the advantages is that very simple to change and modify the code and to adapt from one application to the next, because it in the end only talking a little bit about some variations in the flowcharts, programming 2 or 3 interrupts or changing the directions of some pins, and you have another application very fast and without understanding that much from hardware perspective, and you are able to invent the same kind of application. So those are also good advantages here, okay, to consider when designing that kind of circuits from the engineering point of view. All right, and perhaps the last explanation here that can be considered, you see, is not that one associated to the loop speed, but you know, this phenomena that is occurring here. You have an interrupt every time that there is a falling edge from the clock. Can you be aware of that? I mean, look at this on what is happening if you now keep an eye on the watch. You watch the clock flag. If you are watching the clock flag, what is happening? The clock flag is all the time. You see, you practically don't see it. This is, you see now that time to time is changing. You see, just it's changing now time to time. You see, the system is executing. You see, the system is running, and you know that this only can run if you have this clock flag set to 1, because this is the way you have to tune to the interrupt service routine. So how can you be sure that you have an interrupt every half a second, because this is the clock frequency? How can you be sure about that? Okay, well, you can stop the simulations and you can go step by step, and now you can go down, okay, and try to find the function interrupt. And here, for example, here is where are you saying that the clock flag to be 1. So you click just here after having set the flag. So now if you run, look at this, you have the same as before. You have that the system stops because of the breakpoint, but now if you see the time elapsed, it is 500 microseconds. Exactly what you are expecting, you see? 500 microseconds is the time that's been elapsed and between interrupt callings, you see? So the system looks like that is working perfectly well. Exactly as you have defined in your planning.